At the end of the first half of this lecture, I posed this question where a charged comb repels a bottom piece of tape and attracts a top piece of tape, and the question is simply whether the comb has top or bottom charge. And we've seen that bottom repels bottom, top repels top, and bottom and top attract each other. So since the comb repels bottom charge, it must have bottom charge. To put it more simply, like charges repel and unlike charges attract, and so the comb must have the same kind of charge as a bottom piece of tape. So we have seen that there are two kinds of charge. For now, let's call them bottom charge and top charge, because we've discovered them by looking at the bottom pieces of tape and top pieces of tape. And now we've seen that the plastic comb has the same type of charge as the bottom piece of tape, and so it has bottom charge. I had also charged up a plastic rod and a piece of wool, and if we tested them, we would find that the plastic rod, just like the plastic comb, has bottom charge, and the wool has top charge. But what if there were a third kind of charge? Could there be a third kind of charge? Well, what would it look like? Well, it would be a charge, and so, by definition, it would have an attractive interaction with neutral things. And something carrying this hypothetical third type of charge would have to repel other things with this third type of charge, like charges repel. But, and here's the key thing, it would have to be attracted to all different kinds of charge, and so it would be attracted to both bottom charge and top charge. Well, the fact is, this is never observed. People have done extensive experiments looking for it, and we never observe such a thing. And so we conclude that there are two kinds of charge, and only two kinds of charge. So we know that there are two kinds of charge, but what should we call them? Well, the choice of what to name them is really arbitrary. We could call them blue and gray, or Tom and Betty, or Flurb and Blob. It really doesn't matter, except that there's an experimental observation that gives us a reason to choose a particular pair of names. If you take a top and a bottom piece of tape, and they're both charged, and you test that they're both charged, and you stick them back together. Try not to touch them too much because you don't want to discharge them. What you'll find is that after you've stuck them back together, they're not charged. So recombining them seems to make their charges cancel out. Well, that means they behave just like adding positive and negative numbers. And so we've chosen to name the charge types plus and minus, or positive and negative. But which is which? Which is top? Which is bottom? Well, again, that's arbitrary. There's nothing in the experiments that tells us which is plus and which is minus. This is a choice. So we'll follow the standard convention in which the top piece of tape corresponds to what is positive in the convention, and the bottom corresponds to negative. And this is a convention that goes way, way back to the 1700s when Benjamin Franklin did his experiments on electricity. And it's sort of too bad he didn't choose them the other way around, because it turns out that what flows through wires is negative charges, and that causes some slight inconvenience in our theory later on. Let's think a little more carefully about what happened when we took our bottom and top strips of tape, separated them, found that they had opposite charge, and then stuck them back together again and found that they were neutral. This suggests something. The tape strips started with 0 charge, and after we had separated them and recombined them, they had 0 charge again. And so that suggests that the amount of positive on the top and the amount of negative on the bottom were probably equal, so that they exactly canceled, and we were left with 0. And so the total charge on the top and the bottom throughout this whole process was 0. So we can hypothesize that charge is a conserved quantity, that through this whole process we never created any charge. All we've done is separate positive from negative that was there already, and that the neutral bottom and top strips and tape already contained positive and negative charge in equal amounts. Let's think about rubbing a plastic rod with a piece of wool. We know that they start out neutral, and when we rub them, they're both charged. The plastic rod, just like the plastic comb that I asked you a question about, becomes negatively charged. And so we can infer that if charge is conserved, the wool must become positive. So what the state of the system is after rubbing is that there's some amount of negative charge on the plastic rod, and there's some equal amount of positive charge on the wool. And in this charge diagram, that's what we'll call this, a charge diagram, I've been careful to draw equal amounts of charge. However, remember that before they were rubbed, each of them was neutral because it contained equal quantities of positive and negative. And so we would have had a situation like this, where I've drawn equal amounts of positive and negative in each, and here I'm showing bar charts showing quantities of positive and negative charge in each object. So what is it that happens when we rub them? Well, there are two possibilities. One possibility is that the rod becomes negatively charged because some negative charge from the wool moves over onto the rod. This now leaves the rod with an excess or a surplus of negative charge, and so it is negatively charged, and the wool with an excess or surplus of positive charge. And so the bar chart after rubbing would look something like this. But that's not the only possibility. It's quite possible that what happened was the opposite, where the rod lost some positive charge, giving it to the wool. In which case the bar chart would look like that. Well, which one was it? Which one of these actually happened? Well, in fact, we don't know. All this experiment tells us is that after rubbing, the plastic rod has an excess of negative charge compared to its positive, and the wool has an excess of positive compared to its negative. Either of these is possible, and without doing far more detailed experiments, we can't tell. Ultimately, it comes down to details of surface chemistry that go on at the surfaces of contact between the rod and the wool. Because we don't know which happened, there's very little benefit to drawing this charge diagram showing the positive and negative charges in both the plastic and the wool, because we don't actually know which of these happened. And so this far less detailed charge diagram, where we just show them uncharged by showing nothing on them, and charged by showing positives on the wool and negatives on the plastic, is a perfectly good charge diagram. The only thing to remember when you're looking at a charge diagram like this is that it is not suggesting that the plastic rod only has negative charge after being rubbed. What it's suggesting is that the plastic rod has surplus negative charge after being rubbed, and that may have been achieved by it gaining negative charge from the wool or by giving positive charge to the wool. All through the various demonstrations that I've shown video of, and in any experience that you have with electric forces, you may have noticed that electrical forces are stronger between objects that are close together, or in other words, electric forces decrease in magnitude with distance. I think the clearest demonstration of this in the videos I've shown is with the charged rod attracting the stream of water. We can see from the angle that the water is deflected that that attraction is stronger when the rod is closer to the stream than it is when it's farther away. So at large distance, and let's call this distance r, we have a small electrical force that the rod is exerting on the stream of water, and when we reduce that distance r, we get a larger electrical force. One other thing to point out before I finish up is that objects can have more or less charge. Being charged or uncharged isn't just an on-off thing. Things can have large quantity of charge, or they can have small quantity of charge, or in other words, charge is a measurable quantity. Our indication of how much charge an object has is how strong the electrical interactions are that it has with things around it. And so one of the clearest demonstrations in the videos I've shown has been with the two strips of tape repelling each other. They started off with lots of charge and repelled each other very strongly, and I gradually neutralized them so that we saw them with less and less charge, exerting smaller and smaller forces until they were finally neutral when there was no charge on them. Let me finish up this lecture by just summarizing what we have so far of a charge model. We say that charge comes in two types, and we've chosen, with some good reason, to call them positive and negative. And charged objects are defined as being objects which exert electrical forces on other objects. We see that like charges repel and opposite charges attract, but both types of charge, positive and negative, both attract uncharged or neutral objects. That's something we're going to have to spend some more effort on figuring out. Electric forces decrease in magnitude with distance, and we're hypothesizing, again with some good reason, that charge is a conserved quantity. In other words, we can move it from place to place, but it can neither be created nor destroyed. And finally, we explain the existence of neutral objects, despite the fact that charge can't be created or destroyed, by hypothesizing that neutral objects contain equal quantities of positive and negative charge. And so the way things become charged is that they gain some positive or negative charge from something else, which leaves that thing with a deficit of whatever type of charge it has just lost.